what really makes me excited every day coming to the lab is to really push the boundary of how light and matter interact and how we can harness the new frontiers of light-matter interactions to push the corners of the fundamental physics, as both from understanding some of fundamental questions in symmetry and in the search for new physics, and also looking for emergence of complexity from very normal behaviors of atoms and molecules coming together, and suddenly you have very complex phenomena emerging from it. For example, we laser cool atoms to very, very low temperatures, moving at about 1/1000th of the room temperature, and we load these atoms, thousands of these atoms, in optical traps arranged in a periodical fashion we call it optical lattice. Individual atoms are loaded into these individual optical lattice traps in a way that can be very orderly, that has very little entropy in the system. And we can control the quantum state of these individual atoms extremely well, such that when we are making a measurement of atomic clock, which we're trying to find out the orbital time of electrons moving around nucleus, we take pains to making sure each individual atoms we are investigating that the information we're getting from those atoms are limited only by quantum mechanical rules and not limited by any technical noise. And once we can do that, we can also investigate many thousands of atoms in parallel, so that allows us to gain a lot more signal strength. And as the precision goes further, there's a minute issues of where you're putting more and more atoms in your system. They can have a very weak interactions. And in our case, they turn into strong interactions. The reason being, we were making such a beautiful, precise measurements with all the noise removed from the system. And then when the atoms start to interact with each other, they can turn into systematic issues for our clock. And I always make an analogy that if you have a very little flower that's growing among very tall grasses, you wouldn't see the flower unless the flower grows really tall and you will see a beautiful flower. Or if you cut down the grasses to very, very clean lawn, and then suddenly a very little tiny flower stands out there, is a beautiful physics that we are looking at. And so on one hand, we are trying to push the measurement precision to the next decimal point to really allow us to peel the nature one layer deeper. On the other hand, as you do that, there are unexpected physics that used to be unforeseen. It shows up as a problem, and as a problem in a sense of it could be limiting the accuracy of your clock. But from other people's perspective, some condensed matter physicists, that's actually a very interesting phenomena. You have atoms which are interacting with each other. Suddenly their noise become correlated, and they become a correlated quantum physics. So this experiment, on one hand, we're pushing the measurement precision. On the other hand, you can turn this into advanced material studies. But there are a lot of mysteries out there in the universe, such as the existence of dark matter, dark energy, the fundamental asymmetry between matter and antimatter. So if you are able to build the most advanced, most sensitive scientific instrument and let that sit out there in the orbit of the Earth or in the space, and being able to listen to whether it's gravitational waves or whether the dark matter is passing through in the universe, and then we can detect, because our atoms is so sensitive to any minute changes in space-time fabric or the existence of dark matter, then this turns into a very sensitive instrument for us to try to answer some of the questions that's outstanding at the moment.